Hi, welcome back. This is Rakesh Naik. Today we are going to discuss about the second part in arrays. In the first part we have seen how to declare an array, what is the syntax of an array, what is the meaning of an array, and how we manipulate a single dimensional array. In this talk we are going to discuss about multi-dimensional array. Before we start, a small information. We produce every video in two different languages, Hindi as well as in English. So if you want to view this video in Hindi, kindly follow the link given in the description. And if you have not yet subscribed, kindly subscribe and press the bell icon so that you will get all the updates from this channel. So let us start the second part of arrays, and we are going to discuss about multi-dimensional arrays. We have already learned what is the syntax of single dimensional array. To recall, the data type, then array name and size we write. For example, integer marks within square bracket 8. Similarly, in the two-dimensional array also there is a little change only. We will be writing data type, array name and size 1 and size 2. It means we are defining the size of rows and columns. For example, here integer marks 2, 3. It means we are creating a matrix of size 2 rows and each row contain 3 columns. So let us take an example here. Here mark as the name of the array, and this array contains 2 rows, that is row 0 and row 1, and 3 columns, that is column 0, column 1 and column 2. Here when we are defining mark 2, 3, we can access each and every element by saying mark I and j. I represent the number of rows and j represent the number of columns. Here if I say mark 0, 0, it will indicate the value 10. When I am saying mark 0, 1, it means it is 0th row, first column. So the value here is 20. Similarly, if first row and first column I am taking, the value is 50. So in this way the elements of an array, rather a two-dimensional array, is accessed. Let us try to learn about memory representation. So a multi-dimensional array is presented in memory as a sequence of n cross n consecutive memory locations. Already we know it is a memory location only. This multi-dimensional array are stored in two different representations. One is row measure representation and the second one is column measure representation. Let us see it one by one. What is a row measure representation? It means if a matrix is given of size m cross n, then in a row measure representation we will write the whole data in the form of a single row, but first row I'll write first, then the second row I'll write, then the third row I'll write, till m-1 rows are getting completed. Let us see here. I'll write the first row first, then I'll write the second row, and then I'll write the third row in this way. So according to our nomenclature, it is row 0, row 1 and row 2. You can see here it is a single dimensional array of rows. So if I want to find the address of a particular location, then how would I find? Let us try to see. So the address of element ith row and jth column in a m cross n matrix is calculated as address of a ij, that is base address plus the offset. Base address plus I into n into size of element. What is the meaning of that? It means before the element aij there are I number rows present. So that's why this I. And each row contains n number of elements and each element is having some kind of size. Similarly for this j, it means before the element there are j elements present in that particular row. So j and each of the element will be having a size. You will be able to understand it when we are going to do an example. So let us try to do an example. assume that this is a matrix of marks and now we are taking some integer data type. Let us try to find the location, that is 1, 2. For this location, what will be the address? And assume that the base address of this matrix is 2048. It means what? The address of 008th element is 2048. And we know that each memory element will contain 16 bits because in C++ integer takes 16 bits. So the address of marks 1, 2 will be 2048, that is the base address, and the rest of the part is the offset. It means, what is the location you see? For 60 the location is 1 and 2. It means before 60 there is one row, and on this row before the element there are two more elements. So that's why for this one row I am having 1, and this particular row contains 3 elements in that, and each element contains 16 bits. That's why 1 into 3 into 16. Similarly, on this row itself, before this element 60, I am having 2 more elements. So 2 into 16. So altogether it will become 2128. It means at this particular location I'll find the elements marks 1, 2. Let us take one more example here. I'm trying to find the address of location 0, 1. 0 indicates before this element how many rows are there. 1 indicates on this row before this element how many more elements are there. So we'll take the base address plus before the element how many rows are there? 0 rows are there. So 0, and each row contain how many elements? 3 elements, and each element is having 16 bit. So 0 into 3 into 16. The second part is 1 into 16 because on this particular row how many elements available before this element. So that's why the location for mark 0, 1 will be 2064. Similarly, you can try with some other memory location and find the address of that particular memory location. Let us try to discuss about column measure representation. It means if a m cross n matrix is given, we want to write the elements in a single row of columns. It means first column I'll write as the first part of my row. Second column I'll write as second part of the row, like that till n-1 column gets completed. You will be able to understand when I am to explain this example. So the first column contained 10, 40 and 70. And 10, 40 and 70 I'll write as the first element of the row. The second column contains 20, 50 and 80. These elements will be kept in the same row but as the second part of the element. Similarly, column 2 contains data 30, 60 and 80. These elements will be kept as the third part in the same row. So this is how the column measure representation is done. So let us try to find the memory location. How we are going to calculate the memory location with column measure representation. The formula is almost the same. Address of Aij becomes base address plus offset. Here we will be talking about columns first. That's why base address plus number of columns before the element. Each column contains m number of elements and each element having some specific size. Similarly, before this particular element, how many rows are there, and then the size of the element. So you'll be able to understand it when we are going to do an example. Let us take the element 60 here, the location 1 and 2. And for this particular location, we are trying to find the address. So the base address, let us take, is 2048. That is the address of 008 location. And we are assuming it to be integer. So that's why it will take 16 bits. So address of mark 1, 2. We'll first consider the column part. So 2048 plus before this element how many columns are there? 2 columns are there and each column contains 3 elements. So 2 into 3 and 16 is the number of bits required to indicate each memory location. So 2 into 3 into 16. Similarly, for this element, in this particular column, how many elements are available? So in this column, before this element, only one element is available. So 1 into 16. So altogether 2160. So according to column measure, for the memory location mark 1, 2, the address is 2160. Similarly, for location 0, 1, the address will be, so 0 and 1, first we'll take the column and then we'll take the row. So before this element, how many columns are there? Only one column is there and this column contains 3 elements and each element is having 16 bits. So 1 into 3 into 16. And apart from that, the first part is 0. It means before this element, in this particular column, there is 0 number of element available. So that's why 0 into 16. So the address of mark 01 will be 2096. Similarly, you take other memory location and try to find the address of these locations. So in one-dimensional array, we take one subscript. That is within square bracket, there is only one element. It means I'll write as mark within square bracket 0, mark within square bracket 1 in this way. In two-dimensional, what we do? We represent it in the form of number of rows. In one-dimensional, I can consider this as a row. In two-dimensional, it is a combination of rows. So here, there are two subscripts are required. One for row and another is for column. Similarly, in the three-dimensional array, it is a collection of two-dimensional arrays. You can see it in this way. First one is a two-dimensional array. Second is again a two-dimensional array. Third is again a two-dimensional array. And to indicate that, we need three subscripts. 0, 0, 0 indicates the element 10. 1, 0, 2 indicates elements 130. 2, 0, 2 indicates elements 230 according to this particular example. It means if I am having a n-dimensional array, then I can represent it with a collection of n-1 dimensional arrays. Let us see the operations. Before going for the operation in two-dimensional, let us try to define a class. We are having a class of marks, let us say, and we are having private. In that we are defining three matrices A, B and C, and each of is having size 3 cross 3. And we are defining few simple operations that will be more or less like traversal. Let us see it one by one with the help of an algorithm. Let us see, we are having this matrix, it contains some data and we are traversing. So how the traversal will work? So basically we will traverse with the lower bound, that is we are taking it as I as a variable, and the lower bound obviously is 0, so I becomes 0. When it comes to column, we are taking the variable j, so j becomes 0. Then we are doing some work on aij, that is a00, then j will be incremented by 1. Now j becomes 1. Again we are going to check with the boundary condition whether j is greater than upper bound of j or not. If not, again we will be going to repeat it. Again we are doing some work. Again j is incremented by 1. We are checking with the boundary condition. Again we are repeating. Again doing the particular work. Again increasing j value. After this increment, j value becomes 3. It means this condition holds. It means until now j is greater than the upper bound. So that's why I'll be increasing I by 1. Again coming back to the loop with j equal to 0. So here what will happen? I'll do something with this particular data, that is 1, 0. So this is how I'm going to access each and every element in a matrix. So let us try to see how to print the data. So in place of do something, I'll be giving a cout statement. Instead of this repeat until, I have taken for loop. Void marks, display of mark. I am taking two variables, one for row and another is for column. So for I equal to 0, I is less than row size, I plus plus, j is equal to 0, j is less than row size, j plus plus, I'll print aij element. The inner loop will continue first for I equal to 0. After the exhaustion of inner loop, I will be incremented by 1. Again the whole loop of j will be continuing. Like that, the total output will be getting. The same algorithm I can take for reading the data of matrix. How? So the same thing I have taken, in place of do something, I have taken cin. So for this particular element, I am reading data from my keyboard. So this is how this logic will work for reading, for writing and searching also. For searching, we'll be having a if condition for do something place. Now let us try to see how the searching is being done. For I equal to 0 I have taken, then j equal to 0 I have taken. I am trying to search the element 40, let us say. So within this inner loop, I am making a comparison that aij element means a00 element is equal to the element that I am searching. So I am asking a question here. Is 10 equal to 40? If no, I'll come out of the if statement and j will be incremented by 1. So j becomes 1. And I'll again compare with the upper bound of j. Again I'll repeat this particular loop. Now again j value is 1, I value is 0. So aij value, that is 20. Is 20 equal to 40? If no, then I have to increment the j value. J now becomes 2. I'll compare with the upper bound of j. I'll repeat this thing. Now I am having I value is 0, j value is 2. So aij value is 30. So is 30 equal to 40? If no, again j getting increment. Now j value becomes 3. Now if I am comparing here, j is greater than upper bound, it is becoming true. So that's why I'll come out of the loop and I'll increment I by 1. So I becomes 1. So I'll again go back to this particular repeat statement. At this time, j again will be initialized at 0. Again I'll repeat this particular loop for I equal to 1, j equal to 0. Is 40 equal to 40? If yes, I'll write the variable found to be 1 and I can stop now. Let us see the program for it. So the element is being passed here as a parameter. I am taking three variable I, j and found. Found equal to 0. I have taken this boolean type variable because if I am not finding the value, then it will return 0. Otherwise it will return 1. If the search is successful, it will return 1. So initially I am saying I am taking the found. It is a unsuccessful search. For I equal to 0, I is less than equal to row size, I plus plus. For j equal to 0, j is less than equal to column size, j plus plus. If aij is equal to element, then found becomes 1 and I'll return found. Otherwise, I'll continue the loop. If I am not successful, I'll come out of the loop and return the value. Because the if condition will never be successful, if it is not a successful search, the found will never become 1. found will always become 0. So that's why for unsuccessful search, after the completion of both the loop, it will return me 0. If it is a successful search, it will return me 1 here, and if it is an unsuccessful search, it will return me 0 here. So that is how we are going to search an element in a matrix. So let us try to enhance the algorithm for traversal to find the row sum. The same matrix is given here. Initially we'll take I equal to 0 and we'll start. We'll take one more variable here, sum equal to 0. Now variable j, here lower bound becomes 0 and sum equal to sum plus aij. Aij value is 10 here. Earlier sum we have taken to be 0. Sum becomes 0 plus 10. Here j is increased by 1. So j becomes 1. Now we are again checking with the upper bound of j. It is now. So that's why we are repeating the loop. So the location A01. In A01 we are having 20. Earlier we had 10. Some value we had 10. So when we are at this particular location, we'll be having sum equal to 10 plus 20. So sum becomes 30. So again j is incremented by 1. Now j becomes 2. We are comparing with j's upper bound and again we are continuing with the loop. And when we are continuing with the loop, again we'll reach at this particular place where sum equal to 30 plus 30. So because A02 value is 30. Now j is again incremented by 1, j becomes 3. Now it is satisfying this particular condition, that is j is greater than upper bound. So that's why we'll be printing the value, that is 60. Again I is being incremented by 1. Now I value is 1 and we'll check with the upper bound of I. Now it is not satisfying. So that's why we'll repeat this outer loop. Again we will be taking sum equal to 0 and here at this place it becomes j becomes 0 because j is lower bound we are saying here. So j becomes 0. So we are accessing an element which is this one, that is A10 value. So here the value becomes sum equal to 0 plus 40. So in this way we will be traversing each and every element to find it. Let us try to see the program for it. We are going to translate this algorithm in C++. So we are taking three variables I, j and sum. We are going to print the row sum of it. We are taking a for loop for I equal to 0. I is less than row size I plus plus. We are taking a variable sum here inside the loop itself. And then we are taking j equal to 0. J is less than size of column j plus plus. Now first this loop will be continuing and after the completion of this loop the sum will be printed. After that I will be incremented by 1. I becomes 1. At that time again sum will 0. For I equal to 1, j will be running from 0 to column size. That's how we are going to print the row sum for each and every row that is available in that particular matrix. So thank you for watching this video till the end. In the next video we are going to discuss about more matrix operations like matrix multiplication, like matrix addition, matrix transpose, all these things. So keep watching, keep learning. Till the next video, take care. Bye.